Hello students, today we will discuss about symmetric shared memory architecture. So we are considering the memory where the data elements or the contents of memory can be shared among different processes. So same data to be shared among different processes. So what are the things to be considered when we are doing such type of access? So the normal usage of large multi-level caches we have already seen. If we are having multiple levels of caches, we can have more availability of data, or we can increase the speed by referring to different levels of caches without referring to the primary or secondary memory. So it can reduce the memory bandwidth demands of the processor. Also, the multiple processes may be able to share the same memory. So multiple processes may also it is possible to share the same memory at the same situation. So this is the motivation behind the development of a shared memory architecture for the multi processes. So this particular architecture consists of several processes with a common single physical memory. So if more processes are connected to a single memory, that memory is being shared. So many even if we are having cache in between this, if some common data is to be shared among these two, there will be some issues. So it is always better to have multiple processes who is sharing the same physical memory, but we have to consider several factors also. So we need to have a symmetric shared memory architecture without having any issues. So we need to have multiple number of processes who can share the same memory. If we are having multiple physical memory to be given, the cost will also be increased. So we need to consider sharing a single physical memory among different processes. So for that situation, all these processes are connected to the memory through a shared bus. So the bus is being shared by different number of processes. So you can see this diagram where you can see that different processes are associated with some caches. So closer to the processor we are having some caches. That means a single cache or more levels of caches will be there, and from that it is connected to the main memory, and it is also connected to the IO system. Now if this processor requires some data, it will primarily look into the cache. If it is not available, it will look into the bus. Through the bus it will refer to the main memory. So that data is available within this primary memory. For example, the data is X. But at the same time, if second processor is also trying to access the same data, it will refer to the cache. It is not available. It will refer to the shared memory. But now this data is being given to this processor. So how we can handle this situation? This is the main issue related to the symmetric shared memory architecture. So there are several issues related to the situation. Now this is a shared memory architecture where number of processes are connected to the common bus through which the main memory data can be shared among different processes by considering the several issues that may happen within this structure. So we will see some details. So symmetric shared memory machines support caching of both private and shared data. So this also allows the caching of private data in the sense the private data of all the processes, and also the shared data. That means the data that can be shared among all the processes. Both can be cached on its own caches. That is each of the processes caches, and private data are used by that individual processes alone, but shared data are used by more than one processes and the processes communicate through reads and writes on the shared data with the support of bus. When a private data is cached, its location is migrated to cache. So if there is some dealing with the private data, it is always there in the cache and there is no issue to the processor for accessing that particular private data. The memory access time and required memory bandwidth is also reduced if the private data that is stored in the cache can be accessed by the processor. So we can reduce the overall memory access time as well as the bandwidth also. The program behavior is identical to that of a uniprocessor when we are having a private data being utilized by a single processor. But when shared data are being cached, when the shared data are cached, the shared value is replicated in multiple processes. When the shared data are being cached, so we'll just look into the previous diagram once again. When the shared data to be cached, for example, this H data is added to this cache. Now this H is having a value 10 after the operation of this processor. The value is 10. But here it is 5, for example. This is being accessed here and processor do some calculation and the value became 10. The same time processor, some other processor want to access the H. It is not there in this cache. It will refer to the memory. Now it will be taking this 5 over here, but which is actually wrong because it is being modified this by this processor, that is 10. So that is to be changed here also. So that is not correct. So the access is not correct. Cache consists of correct value. Memory is not being updated accordingly. Similarly, if the data present in the cache, some other cache that also writes some other data based on the same value, there may be some problems because it won't be accessing the correct data each and every time some other processor tries to access the data. So this creates a problem that is called as a cache coherence. What is cache coherence? When data is shared or the shared data are cached, the shared value is replicated in multiple processes. Because of that, the problem that is called as cache coherence may be occurring within this shared memory architecture. So we'll be discussing about the solution of this cache coherence on this shared memory architecture. So we'll see in detail about the multiprocessor cache coherence. So sharing cached data introduces the problem called cache coherence. I have already mentioned that. It means that two different processes can have two different values for the same location. Correct? Two different processes can have two different values for the same location. I have mentioned about it's 5 to 10, but second processor receives 5. So one is having the value 10 and second is having the value 5. So two processes can have two different values for the same location X. So a memory system is coherent. A memory system is coherent if any read of a data item returns the most recently written value. So in the previous case I was mentioning the recently written data is 10 for X. So next processor, when it tries to access that data, it should get 10 itself, not 5, which was early written. So recently written value must be taken by some other processor. That possibility must be maintained so that we can say that a memory system is coherent. So in this aspect, means there are two different aspects related with this memory coherence. One is called as the coherence. It defines what value can be written by a read. What value can be written by a read. A read operation, whether it is returning which value, a correct value or wrong value. And the second thing is the consistency, which determines when a return value will be written by a read. So a data is being written by the processor, but when this value will be returned by another read operation. So these two are actually correlated. Coherence defines what value can be written by a read. Consistency determines when a return value can be written by a read operation. So we will see one example cache coherence problem. We will see one simple situation where we can easily identify the problem of cache coherence. So the first column indicates the time, each time what is happening. Second time the events that are occurring on each of this time. Now this is the cache contents of CPU A. Now assume that we are having two processors A and B. Two processors are there, two CPUs are there. This is the cache content of A, this is the cache content of B, and this is the primary memory content. Okay, so now we are discussing about the memory content H. We are having a memory content H. Okay, so in these different timings, what are the things that are happening? When does this cache coherence problem occurs? Okay, the time 0, no event happens. We are having the value 1 in the memory location. H is having the value 1 in the memory location. Okay, initially we are having that value there. Now at time 1, CPU A reads H. CPU A reads H. It will be trying to read the value H. So CPU A reads H means it is trying to access it through the cache. It is not available there, so it will be getting the value from the memory and it is stored in its cache. So it will be reading the value as well as it will be storing the value into the cache of A. Okay, so CPU A is simply reading the value 1 H. Okay, then next time 2, CPU B reads H. CPU B reads H, what will happen? At that time, what is the value of CPU A cache? It also consists the same 1 is there. Now here previously when A reads H, nothing is there in CPU B cache. So now it reads 1 from memory and its cache now consists of 1. Okay, so now CPU A cache consists of 1, CPU B cache also consists of 1. Now what is happening is, now CPU A stores 0 to H. CPU A stores 0 to H. It changes the value of H to 0. What is happening? CPU A stores 0. So along with the cache, it will change the value of H to 0. Okay, so it changes to 0. It changes to 0 here. But at this time, there is no change to the cache of CPU B. It is having the earlier value, that is 1. Because CPU A stores 0 to H, it will store 0 to H. Its cache also changed. But B, that is already taken the value of H previously, will remain the same value 1, because it doesn't know that whether there is any change or any value change happens to the memory content H. But next statement, if somebody is trying to access if B is trying to access H, it will be getting the value 1 which is there in the cache. So first access is towards the cache, but which is actually wrong, because the value of H is now 0 but it is getting the value 1. This is called as the cache coherence problem. So the cache coherence problem for a single memory location H, read and write by two processors A and B. I think it is very clear now. Okay, so immediately every processor will be trying to access the content from the cache, but if the cache consists of a wrong value, the value is actually being modified in the primary memory, but if the cache consists of a wrong value, it will be trying to access that value only. That means it is getting a wrong value. Okay, so that is to be managed, or that is to be controlled by using some mechanism. This is actually called as cache coherence problem. Now we can define a memory system is coherent if a read by processor P to location X followed by a write with no other write of X by another processor always return the value written by P. Okay, so you can imagine on the situation, a read by processor P to location X, we have seen in the previous example, followed by a write. A was writing something with no other write of H by another processor, always return the value written by P. Okay, so whatever value that is currently written by P must be always written, not by any previously stored value. Then only we can say that a system is coherent. Previous example, 1 was written by processor A to memory X. 0 was written, but uh, if some other access by B will always access only 1, which was written earlier, but it should always return the last written value, that is the current written value must be retained by any other processor which is trying to access the same data. Similarly, a read by processor to X followed by write of another processor returns the written value if read and write are separated and no other write occur between the access. The same thing. Writes to the same location are, so if two processors are trying to write into the same location, that must be maintained an order. It must be serialized, that is one after another. Two writes to same location are seen in the same order by the processors. Okay, so then only we can say that a memory system is coherent. Now we will be discussing about the different schemes for enforcing cache coherence. Now, coherent caches provide migration of values, as a data item can be moved to a local cache and used there in a transparent fashion. So, movement of primary memory to cache memory. So, coherent caches must maintain a movement of data from cache to primary memory as and when it is required. So this migration reduces the latency to access shared data item that is allocated remotely and the bandwidth demand on the shared memory. So because of this migration, it reduces the total memory access time to access the shared memory content. Similarly, coherent caches also provide replication of shared data that is being simultaneously read, since the caches make a copy of the data item in the local cache. It provides replication for shared data as it is having the value in the primary memory as well as in the cache memory, and the same will be on different processors also. And it can be simultaneously read by different processors. And this replication reduces both latency as well as the contention of data that is shared among different processors. So the different protocols used to maintain this cache coherence is usually called as cache coherence protocols. So they are actually implemented by tracking the state of the shared data block. For example, the block which we are using in the previous example was X. So by tracking the different states of that memory block, we can maintain, we can use some protocols which is called as cache coherence protocols. So there are two classes of protocols. One is called as directory based protocol and second one is called as snooping protocol. The first category, that is directory based protocol, it is sharing the status of block of physical memory is kept in one location, that is called as a directory. So the directory based protocol follows the mechanism of maintaining a single directory where it is maintaining the status of the block of memory that is being shared. So by looking at that single directory, everybody can understand that what is the current status of data. That is actually called as directory based protocol. So that we will be discussing in some other presentation. Here we will be focusing on the next mechanism, that is called as snooping protocol. So what is happening with the snooping protocol? Every cache with the copy of data from block of physical memory also has a copy of sharing status. So every cache with the copy of data. So if processor P1 is having a copy of data, it should also have the details of its sharing status. What is the current status of that particular data? What is the, whether somebody else is being written that data, somebody else is being modified that data. That status information must be there with all the cache memory associated with all the processes. So the caches are connected to the common shared bus. So we are using a specialized bus to which these caches are connected to the physical memory. And as you know, all the cache will be having its cache controllers, and controllers, monitors or snoops. They look into the bus to determine whether the data have the copy of block that is requested by bus or processor. So always maintain, always look into the, or always monitor into the bus, so that the cache, whether the cache consists of the updated data. So the processor cache in association with the common bus connected to the physical memory, they are maintaining a protocol so that it can always, all the caches can always have the status of the different memory blocks, and accordingly it can have the access to the most recently written or the most accurate data that are currently eligible for accessing that particular data. So we will see in detail about snooping protocol. So it is done in two different ways. The snooping, the coherent requirement of by using snooping protocol is based on two different ways. First one is called as write invalidate. So we should invalidate write invalidate. Okay, so this, let's listen to the term write invalidate. Okay, so let us see what is happening. It ensures the exclusive access to a data item before it writes that item. It ensures the exclusive access to a data item before it writes that item. Whether it can exclusively write that data. So it ensures that exclusiveness. If somebody else is using that, it cannot be exclusive now. Before writing some data, it should ensure that it is having an exclusive access to that particular data item that is to be written. Now, what is the meaning of this exclusive access? This exclusive access ensures that no other readable or writable item exists when the write occurs. So, if this processor is having that particular writing, that exclusive access, it should ensure that no other readable or writable item exists when that write occurs. Okay, so if I am writing the value of x, all the x value must be invalidated. That is the main purpose of write invalidate. That means it invalidates other copies on a write. So in the previous example, if x was initially 5, one processor modifies that to 10. Okay, so when it tries to write that it's to 10, when it tries to write that 10, it must invalidate all. So some other process will be having the value 5. All of these must be invalidated so that only this is the valid data. So this must be done with the support of the bus connected to the different processes. Since the write requires exclusive access, any copy held by the reading processor must be invalidated. All the other processes which is having the value for that particular X or that particular block must be invalidated so that no other processor can have access to the wrong data. It should have the access to the currently written data only. So if somebody is trying to write a shared data, it must invalidate the previous value of all the caches currently available with any of the processor. When the read occurs, it misses in the cache. If it is trying to read, if it is misses in the cache and is forced to fetch a new copy of the data. Okay, it will be taken from the primary memory. Now, if two processes try to write at the same time, one of them wins the race and other process, so some order will be maintained there. That is not an issue. For other processor to write, it must contain new copy of data which is having the updated value. If other processor for other processor to write, it must contain new copy of data which is having the updated value. So every time when a new write is happening, it should have the means the data that is to be written must be the updated value. Hope it is very clear. So when somebody is trying to write, all other previously written data of that block item must be invalidated. That is the only thing to be done as part of write invalidate mechanism. So here you can see an example of write invalidation. Okay, so first thing, CPU A reads sets. It is not in the cache miss. So this is the bus activity. Bus consists of 0. So initially the content of H is 0. CPU A reads sets. It is not in H. Now H consists of 0 and it will be moved to cache also. It will be having the value 0. Now CPU B reads sets. It is not in B's cache. Okay, so it will read that from primary. So its cache consists of 0. A is already having 0. So now both CPU A and CPU B cache consist of 0. Okay, clear. Now CPU A, first CPU writes 1 to H. Now it was 0, it is trying to write 1. It will write 1. That time the bus associated with that will invalidate H. All other H, all these H value associated with B will be invalidated. So this will be invalidated. So that is why here B will be invalidated. There is no value. Now it is writing a 1 to H. Okay, it is writing a 1 to H. So CPU here writes a 1 to H. It will invalidate all the H. It will write 1. Then CPU tries to read H. It will be reading the value 1 that was written now by the CPU A, because it is not there in cache B, because CPU B cache nothing is there, it is being invalidated. So it will automatically take it from the primary memory so that it will get the value 1, that is the correct value. And CPU A cache also consists of the value 1. That's it. Very simple concept. When somebody is in a processor tries to write some value, the bus will be active now. It will invalidate all the currently written value of that particular H. So now that is having the exclusive access to that write. It will write that value. Then everybody will be getting this value later. So there won't be any issue of getting wrong information from the local cache that is associated with any of the processor. So very simple thing, write invalidate is the first technique that is associated with the snooping protocol mechanism used for cache coherence problem. Now the second thing is write update or broadcast protocol, the second stage. Write update or broadcast protocol. It updates. So while writing, what we are doing, it will invalidate all other current X. Now second stage, it should update all cached copies of data item when that item is written. So if that item is written, so 1 is written by A. Now the new value must be updated on all the cached copies of the same data item, that is by different processes. That means it broadcasts all writes to all the shared cache lines. So this is second mechanism where we can apply with the snooping protocol. It will do update all the cache memory. So what is happening is through this bus only, it should go to all the processor cache and it should update that. So it consumes more bandwidth. It will take more time to do all this operation. So because of this, most multiprocess use write invalidate protocol. So snooping protocol can be done by using write invalidate and write update. Write invalidate simply invalidating all the write of the current data item, but write update while changing one data item simultaneously all the data item present with all the caches must also be updated. So that is a difficult task. It consumes more bandwidth and time, so it will affect the entire performance. So mostly we are following the write invalidate protocol mechanism for the snooping protocol mechanism. So the basic implementation. So the invalidate protocol can be implemented by the use of a bus or can be used by other broadcast medium to perform invalidates. So either by using a bus or by using some other medium, we can do the invalidate operation. To perform an invalidate, the processor acquires a bus access and broadcasts the address to the to be invalidated. It's very clear. So just giving an implementation details of the same mechanism. All the processors continuously snoop on the bus and check whether that address is in their cache. So every time all the processors are continuously monitoring on the bus that is connected to the primary memory, and it will be checking the status of each of this data item. If so, then the corresponding data in the cache is invalidated. So it will always look into the bus. If two processors attempt to write shared blocks at the same time, their attempts to broadcast invalidate operations, they will be, that is already described. So either the first one or second one will be, so there's some order will be automatically maintained for providing that writing. The normal cache tags can be used to implement the process of snooping. So there will be some tag associated with each cache, so that we can do monitoring on a particular bus. So we'll be having a valid bit for each block, makes invalidation easy to implement. And also to track whether a cache block is shared or not, an extra state bit is added which is associated with each cache block. So when a write to a block in the shared state occurs, the cache generates an invalidation on the bus and marks the block as exclusive. This is what is happening, what I was mentioning before. Then no further invalidation will be sent by processor to that block. Currently, the processor with sole copy of a cache block is called owner of the cache block. So currently, whichever processor is doing that exclusive write, which will be having the sole copy of a cache block. So when an invalidation is sent, the state of owner's cache is changed from shared to unshared. Similarly, if any other processor later requests this cache block, the state is made shared again. So until no other processor is giving a request, it will be in unshared mode. Whenever somebody is giving a request to that particular data, it will be changed that into a shared thing. Now an example situation is given. A snooping protocol is implemented by incorporating a finite state controller. So there will be a finite state diagram that represents the control between these stages, like exclusive or access and all. And this controller responds to requests from processor and bus and then changing the state of the selected cache block. The controller also uses the bus to access data or to invalidate it. All things are already mentioned. So it will be having three states. One is the invalid state, the second one is the shared state, and third thing is the modified state. So it is the translation between these three states. That is why it is called as finite state controller. Shared state indicate that the block is shared, and modified state indicate that the data is being updated in the cache. So these are the different examples of different request process and the bus request. So for example, I'll read one or two. There is a read hit. The source is processor. It will be in shared or modified mode. So it will say normal hit, read data in the cache. So different stages are given here. So for example, invalid, I'll take this. Write miss, data is not there. Processor is providing that state is invalid, so it is a normal miss. Place write miss on bus. That is the procedure for each of these stages. I'll take one more thing, a modified. A write hit is there given by the processor. The state is a modified thing. It is a normal hit, write data in cache. Okay, so in various requests. Accordingly, it is by different processor we are doing all these operations based on this invalid, shared and modified situations. Now in the case of the source as bus, when a read miss occurs in the shared mode, it will allow memory to service read miss. Directly it will go to the memory. And read miss, it is a modified mode. The action is there will be an application of coherence protocol. Invalidate, there is an attempt of coherence. Similarly, it is doing all these operations related to the cache coherence protocol. So basically you have to remember about the write invalidation and write update. Write invalidation, how it can be done by using some simple examples. So these are some of the example requests by the sources like processor and bus, and accordingly how the cache will be performing, and the operations that happens during this request by various sources. Now a state diagram is given that is used with write invalidate protocol with write back cache. Okay, so we can see there are three stages. One is the invalid stage, shared and exclusive. So between these three, this communication happens. The CPU read, then place invalidate, exclusive read or write, then from invalid to write, place to write, that is exclusive. So it is between these three. Okay, so different stages are happening between the same previous diagram is means the table is shown in the state transition mode. So these are the cache state transitions from invalid to shared, shared to exclusive, then invalid to exclusive, exclusive to shared. Between these three this happens. So cache state transitions based on request from the CPU, this is, and this is the cache state transition based on the request from the bus between exclusive to invalid, exclusive to shared, and from shared to invalid. In this way it is happening. So both the processor and bus together will do the updations or invalidation of the data present in the cache memory when we apply the snooping protocol for managing the cache coherence problem. So by avoiding this, by using this cache coherence protocol, that is the snooping protocol, we can reduce the problem of cache coherence, and we can have the updated data, and that can be selected from the that can be accessed, and the system will be working in a better way for the response time as well as the bandwidth of the entire system. So that is all about the cache coherence protocol. Snooping protocol we have discussed now. Directory based protocol will be discussed in another session. So that is all for now. Thank you.